right, it is time for laws of the logarithms. So this is a combo of 5-5 and 5-6. Bonus work here. We're going to be expanding, condensing, and solving. I don't know what these hand motions meant, but we're going to be solving it as well. So a little combo. You've seen some of this before in Algebra 2 Honors. We're just going to expand upon it. No pun intended. We're going to expand upon it. There's going to be some spicy problems here. I'll tell you what. All right, let's go for it. But first, remember what our logs consist of. We have a log. We have a base. The argument, we can refer to it as, is inside the parentheses there. It's got to be greater than 0. That's important. It all equals an exponent. You'll often hear us say logs are exponents. Log is an exponent. Exponent, exponent, exponent. So what kind of properties do you think logs follow? Exponent properties. Let's do it. So here we go. You're going to want to pause for this to jot it down because I'll probably go a little bit faster than you can write. Let's see here. We got log base b of m times n can be expanded into log base b of m plus log base b of n. Okay. And these work both ways here. Flippy floppy. Okay. So I can go from a sum to a product to a sum. What happens when you multiply like bases with exponents? You add the exponents. When you're multiplying like bases, you add the exponents. Multiplication, addition, they went together. Go figure. Our example here would be log base 3 of 9 plus log base 3 of x. And if you're asked to then simplify or evaluate when possible, log base 3 of 9, 3 to what power gives me 9? 2. So it'd be 2 plus log base 3 of x. Look at that. The 2 is the exponent there. 3 to what power? 3 to what exponent gives me 9? 2 does that. So this would be my fully simplified, but you can see the expansion with the previous. All right, quotient. When we're dividing, we can expand that to subtraction. Much like when we're dividing like bases, we subtract the exponents. See? Cool. All right, so I'm going to have log base 1/4. What a terrible base. Of 4 minus log base 1/4 of 5. And again, if this asks us to simplify or evaluate when possible, well, 1/4 raised to what power would give me 4? That would be -1 minus log base 1/4 of 5. Right? 1/4 to the negative first power would give me the reciprocal of 1/4, which is 4/1. There it is. All righty. So again, that's a fully simplified, evaluated version of it. Power to a power. What happens with exponents when you have a power to a power? You multiply the exponents. Likewise here, if we have log base b of m raised to the p, we could bring that out as a coefficient, right? Multiplication between them. So what I could have is then x times log base 2 of 8. And once again, if you can simplify, let's go for it. If we can evaluate, log base 2 of 8, 2 to what power gives me 8? That'd be 3, so I'd have 3x would be my final here. All right. This is great. This is great stuff. I love this. It's awesome. Okay. Equality. So if log base b of m equals log base b of n, then we know that the arguments, what's inside the log, m and n, should be equal to each other. So in this case, when I have a log equaling a log, same base, only with the same base, it can't be log base 8 and log base 7. That does not work. It has to be the same base. I can have 3x minus 4 equals 5x plus 2, and I can solve that. I'm going to get 2x over here. If I subtract, I'm going to get -6. So I get x is equal to -3. But in these situations, we do need to check to see if this will work, right? We do need to check, make sure everything works in here. What do we mean by does it work? Is the argument positive? Remember it said the argument needs to be positive right here. We can't take the log of a negative, can't take the log of 0. It needs to be a positive non-zero number. Okay, well, if I plug, so -3 is negative, but that doesn't really, that's not what decides this for us. What decides it is when we plug it back in. If I plug -3 back in, I get -9 minus 4 is -13. No bueno. Okay? 3 times 5 is negative 15 plus 2 is negative 13. Although I get negative 13 and negative 13, I can't take the log of a negative. So that's an extraneous solution. It actually has no solution here. Okay? Main concept, though, is that we can set what's inside the log, the argument. We can set those equal when they have log of the same base. Okay? Beautiful. Fantastic. Wonderful. All righty. A couple more here. Actually, a couple more repeats, but the top one here, exponential logarithmic inverse properties. Whew, that's a mouthful there. Log base b of b raised to the x. So when the base and the argument are the same, I'm going to switch up colors. I've been going green this whole time. I mean, green is my favorite color. But I'm going to go, there we go. We're going to go with that. So what's an example of that? It'd be like log base 3 of 3 raised to the x. Well, by my power property, right? Look at this. We're already using these properties. I can bring that exponent down as a coefficient. Let's do that. So I would have x times log base 3 of 3. Well, what is log base 3 of 3? Log base 3 of 3. 3 to what power gives me 3? 1. So this is equal to 1 times x, which is just x. That's what we see here. So when you see log base b of b, log base some number of the same number raised to the x, you know it's just going to be, boom, x, or whatever that exponent is. Some people think of like, oh, it just like cancels out. I don't like to think of it as like cancels out. I mean, it does go away because it becomes 1, and multiplying by 1 doesn't change anything. But again, it doesn't really cancel, okay? It does go away, but that's not canceling. All right, moving on. Next one here. Let's say I have, let's go with another color here so it doesn't get too crowded. I'm going to go with orange. So here I could have 2 raised to the log base 2 of x. Well, what's that going to equal? That will once again just simply equal x. It's the 2 raised to the log base 2. It's not canceling. It does go away. And how about I'm going to show you why. Because I feel like sometimes we get these rules and we're like, why does it even happen? Just magic? Yeah, it's just magic. The magic of Pythagoras. No, I'm just kidding. So let's take a look here. I'm going to set this equal to something else. Let's say I don't know what it's going to equal. I'll call it y. So this is currently in exponential form. 2 to a power equals y. I mean, it's a real ugly, terrible, there's a log in the exponent, but it's exponential form nonetheless. Let's change it to log form. I would have log base of the 2, right? So log base 2 of y is equal to the exponent, right? The logs are equal to the exponent. My exponent just happens to be log base 2 of x, okay? So I did my little swoop. Whoop. Log base 2 of y is equal to the exponent. Well, what happens now? Look at that. 1-to-1 property. So I get y is equal to x. Sorry, I had to sneeze there. Y equals x, right? Well, there we go. There we have it. Y is equal to x. That means that I could substitute in to that statement there, right? It all equals x. Okay, so that's really what's happening there. There is a bit of algebra behind that one. I think most of us just remember it's like, oh, I see the like things and it just kind of goes away magically. There is math as to why. There's rhyme to the reason. All right, 1-to-1 property of exponents. We've already seen that one. B to the x equals b to the y. The exponents are equal. The 1-to-1 property, we literally just used that. And then change of base formula. This is handy if you have a TI-83 or you don't have the alpha math feature, the log base feature on your calculator. You could type in, so if you had like log base 4 of 16, I could do log base 10. It would be your built-in. I'm going to, there we go, move it back a little bit. Log of 16 divided by log of 4. You can just plug it into your calculator like that. So that was very useful in some of the older model calculators. A lot of us have the TI-84 now, but if you have an 83 that you're using, you don't have the log base feature, so you do need to use change of base. Boom, there it is. Fantastic. We got all the properties. Now it's time to use them. All righty, let's do it. So a couple simplifying type of examples. So within our problems, we're going to see we're going to have to simplify. We're going to have to evaluate within expanding and condensing. So for the first one here, we have log base 2 is 16. That reads 2 to what power is 16? You should be able to do this by hand, not with your calculator. 2 to the 4th power is going to be 16. Logs are exponents. 2 to the 4th power, exponent 4. Boom. All right, this next one here, log of 1 over 10,000. Well, let's remember that when it's just written as a log, it's implied that it's log base 10. And then, I got an idea. 10,000, 1 over 10,000 can be written as 10 to the negative 4th. Now I can use that property right up here, the exponential logarithmic inverse properties that you totally remember the name of, right? We can use that here, and we're just going to have negative 4. Awesome. Nice. Let us keep moving. So for this one, I put some parentheses around it because I thought it was a little bit confusing. It looked like it was just the 6 by itself. The whole 6 root 6 is the argument there. So what can we do? Well, oftentimes it can help to write a radical as an exponent. I'm going to do that. So we'd have log base 6 of 6 multiplied by 6 to the 1/2. And now that I have exponents, I'm going to throw a 1 up here. That's a terrible 2 there. There we go. It's a little better. Well, if I have like bases, let's just look at the argument right now. If I have like bases of 6, what can I do with those exponents? I can add them, right? So I get 1.5 or 3/2. So if I have that, I once again use that same property from above and get 1.5. Or you could say 3/2. Either, not 3/3. 3/2. Either one of those is fine. Cool? Awesome. Moving on. All right. Time to write as a sum or difference. So we're going to go ahead and expand here. Now, I know you see addition and subtraction in this one, but they're inside, they're binomials there. So I got to expand this one. Well, it's multiplication between, so to separate that, to expand it, I'm going to do addition. So I will have log base 3 of x minus 1 plus log base 3 of x plus 2, and it would be squared, but I know that exponent can come down as a coefficient. I'm going to pop that right in front there. This one is expanded fully. We are donezo. Okay, at this level, pre-calc honors, you should be able to bring that exponent out front in the same step. Okay, if not, it's okay. Write it all down, but I'm going to bring it out in one step. This one, I've got multiplication up in my numerator. I have division. Okay, so when I expand this, I'm going to be involving multiplication, or I'm going to be involving addition and subtraction. Let's do it. So for the first one, with my x squared, I can think ahead and be like, okay, well, if it's log base 5 of x squared, I'll throw that 2 in front. Same with my y, I'll have plus 3 log base 5 of y minus, and then it's a funky minus, what is my coefficient? Or sorry, what is my exponent if it's the square root of z? That's to the 1/2. So minus 1/2 log base 5 of z. There we go. We are donezo. Any questions? It's a video. You can't ask questions right now. I'm just being crazy. I can ask you questions, though. Like, can you condense? Let's do it. No calc. All right? Condense and evaluate. Evaluate impossible. It's not always possible to evaluate, but sometimes. All right, so I have log. There's nothing there. What does that mean? It's a base 10, in case you need that. Lovely. So we're going to pop this all into one log base 10, or just log. I'm going to write the base 10 just because. Okay, now I've got subtraction going on, which means we're going to have some division here. And since these are negative and negative, like negative exponents, they're going to go down to the denominator. So we'll have 3 divided by, and then it'll be 6 and 5 down here in the denominator. Cool. So I can continue, though, with this. I'm going to have log base 10. I have 3 divided by 30, which would be simplified down to 1/10. And 10 to what power gives me 1/10? You'll see why I like to write the 10 base. I think it's helpful to see that when we're trying to evaluate this. I'm going to get -1. Whoo! That's pretty cool. I like that. All right. Very nice. So again, negative negative, they end up in the denominator, multiplied together when we're condensing down there, right? The subtraction is the division. It's really showing me it's going to go to the denominator. And since both were negative, I put them together down here in the denominator. All right, next one. Let's see here. I cannot condense these two yet while this 2 is in my exponent. So I'm going to, or in my, as a coefficient. So I'm going to bring it up as an exponent. I'll have log base 12 of 6 squared plus log base 12 of 4. Okay, so now I have, that's 36. And then I guess I can write that step out. Now, how do I put these two together? Well, I'm going to run out of room off to the right, so I'll go ahead and down here. If it's addition, then they become multiplication when I put them together. So that's log base 12 of 36 times 4. Well, 36 times 2 is 72. Double that, that's 144. That's all I'm doing in my head. And I know that 12 to what power gives me 144? 2. Whoop. Done. That was great. Condensing, evaluating. It's so satisfying when you get one single number, right, instead of some mess. Wonderful. You're welcome for that. All righty. Woo. Fraction out as a coefficient. I just got chills. I was so excited. All right, so I'm going to bring that up as an exponent, which is going to give me log. It's a base 10, right? For now, I'll forego writing it just to save a little bit of writing. And then we have log of 5 squared. I brought that as an exponent. Okay. Now I'm going to write 64. Some of you might be like, I know the cube root of 64 is 4, or we could write it as log of 4 cubed to the 1/3 plus log of 25. So now we know with our exponent properties that those two when multiplied together gives you 1, right? So I would get log of 4 plus log of 25. Now I'm ready to put these together, condense them. That's going to be multiplication when I put them together. 4 times 25 is 100, and I think now I'm going to jot down that base at 10 because that's going to make me think here, well, okay, 10 to what power gives me 100? That is 2, and that is my final answer with that one. Man, I'm loving these problems. These are great. These are fantastic. All right, now what? E raised to the natural log of 1/2 x. If you remember, E and natural log, they're inverses of each other. They undo each other. And our final answer is going to end up just being 1/2 x. Now, I do want to show this in one other way here. Natural log is log base E, right? So E raised to the log base E of 1/2 x. Now, that may look very similar to one of those inverse ones, right? One of those properties we had above. E raised to the log base E, we know that's going to go away. I'm going to be left with just 1/2 x. There it is. So you can remember that, like, oh, if I see these two right next to each other, right, they will undo each other. They're inverses of each other. If there is a coefficient in front of the natural log, you do need to bring that up as an exponent. You can't remove the E in natural log when there's a coefficient in front there, okay? So we might have an example like that later. Moving on. It's like I could predict the future. 3 as a coefficient. What should I do with that? Zoop. So now I have E raised to the natural log of x to the 3rd power. Now those two can undo one another, and I'll be left with x cubed. Dunzo. Awesome. Awesome sauce, as they say. Next one here. Natural log, and then how about I bring that E up and change my exponent to a negative? Now, again, when you see those two together, you're like, hey, those go away. And yes, you are right. It's going to be -4 for our final answer. But if you need a little bit more justification, you're like, Mr. Allen, I don't believe you, bro. Not your bro, okay? But nonetheless, I will show you because I love math that much. Natural log is log base E of E to the -4th. And now we can see once again this situation going on here where it's a log base of that same base. The argument is equal to the base. They end up going away, right? And we're just left with -4, right? Because that's log base E of E is just 1. And that -4 could have been brought out as a coefficient. Moving on. Let's do a little bit of solving, and I'm gonna change colors here. I'm gonna go with red. Okay. I've got two natural logs on the right-hand side. I can't use one-to-one property like that, but I could condense first. Let's do it. So I'm gonna have natural log of x squared minus 8 is equal to the natural log of, what do I do when I condense with addition? I multiply. So 2x. Now I can use one-to-one property, and I'll be able to set my arguments equal to one another. And now, what do we do? What do we do? You should know this, okay? I often see people that are like, oh, I'll just like start square root and things like that. It's like, what? You have a quadratic. Set it equal to 0, factor if possible. You know what I'm saying? So I'm going to do that. So I'm going to subtract 2x off x squared minus 2x minus 8 equals 0. What multiplies to negative 8 and adds to negative 2? That'd be negative 4 and positive 2. And now I'm going to get x equals 4 and x equals negative 2. But remember, we do need to check and see if this will still work, hold true, right? Okay, so I've got, if I plug 4 in, I get 16 minus 8. Cool, that's positive. If I plug 4 in here, it's positive. We're all good. This one is set. Negative 2, however, when I plug it in here, I get a negative because it'd be 4, positive 4. Minus 8 is negative 4. Over here, I'd get a negative as well. That's no bueno. So this one is extraneous. All right, but I do want to make up another scenario of this where, depending on how you start, it can actually, both answers could have been true. So let's say I have this example over here in purple that I made up, okay? As you can see, it has the same type of stuff going on, right? I'm already set up for one-to-one property. So let's go for it. I would have x squared minus 2x is equal to 8. And once again, you would see that the same quadratic would unfold here. It will factor the same, and I will get x minus 4, x plus 2 equals 0, and I'll get x equals 4, and x equals negative 2. I need to now plug it back into the original problem, which is this one this time. If I plug in 4, I get 16 minus 8 is 8, all good there. If I plug in negative 2, I get 4 plus 4 is 8, all good there. So in this situation, both answers work, and in this situation in the red, only one of the answers work. You have to plug it back into the original problem to see if the argument is greater than 0. Okay, this one just happened to work out, whereas this one did not. Okay, so you have to check it. It's not about whether or not the x is negative like it was here, and this one was positive. Yeah, a lot of times it does work out that way, but the x can be negative and still work in the original problem. It's about the argument being 0 or greater than 0, not the x value being greater than 0. Okay? All right. Sorry, I took a little bit of time to do that, but I think it's very important and hopefully will alleviate any mistakes. This next one here, I got 2 logs on one side, but not on the other. I'm going to go ahead, I'm thinking I'll condense those. So I'll have log base 7 of 2x plus 16 is equal to 2. Now, I can't use one-to-one property, but perhaps I could loop and swoop this bad boy into exponential form. So I'd have 7 raised to the second is equal to what was inside the log there, the argument of the log. And now I've got myself a lovely little algebra problem, don't I? So I got 49 equals 2x plus 16. If I subtract 16, I'll end up with what? 33. And if I divide by 2, I've got 16.5 or 33 over 2, so x equals, I'll go with 16.5. That seems nice. Lovely. We're going to keep going here. I know this is it's getting a little lengthy, but we are covering a couple sections here, but they go together so nicely, you know, like peanut butter and jelly. Okay? Let's keep going. All right. There are a few ways of solving this. I'm going to go over the best way of solving it, in my opinion. Just kidding. Everybody got, you got your own opinions on these things. So we could expand this. We could bring a log over. We could do, I think I'm just going to go ahead and write this in exponential form. I've got 8 to the 0 power is equal to x plus 3 over 3x plus 5. Well, that's just going to be 1 equals x plus 3 over 3x plus 5. So if I multiply by my denominator, 3x plus 5, I'll end up with, or you can even think about this if it helps, if you like cross multiplication. You got to do the sound effects, though, if you're going to do that. I'll have 3x plus 5 equals x plus 3. And then I'll have 2x equals what, negative 2. X equals negative 1. A negative. We must reject it. No. We got to check it before we reject it. Okay? If I plug negative 1 in, I get positive 2 in the numerator, and I get positive 2 in the denominator. I'm taking the log of a positive number. We are Gucci. Okay? I don't know why this one didn't have parentheses, but the other one did, but yeah, whatever. So this works. We're all good. I will say on another option was expanding it that I mentioned. Maybe I'll write that out and you can see how it'll work out the same. Oop, that should be minus. (3x plus 5 equals 0. I'm missing a parenthesis. So now if I add the log base, the second one over, I'd have log base 8 of x plus 3 equals log base 8 of 3x plus 5. And then we can use one-to-one property, and then we would be able to set the arguments equal to each other, which is exactly what we have right here, and we'll get x equals negative 1. So either way is fine. If you thought about expanding and bringing it over, that works. I chose to go to exponential form. You know, there's different ways of doing these things. We don't have to fight over it, okay? We can just agree to disagree on what the best way was. All right, we're about to get cray on this one. This one's a little challenging. I like it. Write as a single logarithm. How the heck am I going to write that as a single logarithm if the one isn't even a log? What are you insane? Like, how's that going to work? Oh, I got an idea. Remember how we had the, if I had this, log base 3 of 3. What is log base 3 of 3? That's 1. What can I multiply by and it won't change anything? 1. So what if I were to multiply that 4 by log base 3 of 3? I multiplied it by 1. Did I change anything? No, I didn't change anything. Multiplying by 1 doesn't change anything. So we're cool, right? We're all wonderful. So right now, I didn't change anything because this is a clever form of 1. Okay? I like to say that, clever. Reminds me of Jurassic Park. Clever girl. When he's talking about, I think, the Velociraptor. Anywho, so I've multiplied by a clever form of 1. Now I can bring that 4 up as an exponent there, log base 3 of 3 to the 4th plus log base 3 of x. And now I can condense these. I can bring them into one log, which would be log base 3 of 3 to the 4th times x, which is log base 3 of 81x. 3 to the 4th is 81. You should know that. That's a wonderful thing to know. 3 to the 4th. All right. This next one. 2 to the 4th. Wait, 2 to the 4 plus log base 2 of 5. My goodness. I didn't even say it right the first time. It's so crazy. Okay, well, let's see if we can tackle this one. So that is all in my exponent. I have two things that are added together in the exponent, right? What was going on when we add exponents together? It's multiplying like bases, right? If you multiply like bases, you add exponents. Okay, so I'm thinking about that property right now. When I multiply like bases, I add exponents. Could I go back the other way? Meaning, could I say 2 to the 4th multiplied by 2 to the log base 2 of 5? So we're just looking to evaluate this. We should get a single number at the end. No calculator, okay? Otherwise, it's cheating. So I'm multiplying like bases, where I would add the exponents. So this is equivalent here, right? Now, 2 to the 4th is 16, and 2 to the log base 2, that would just go away. I would just be left with the 5. So 16 times 5 is, I think, 80. Yeah, because 6 times 5 is 30, and 10 times 5 is 80. Or sorry, 10 times 5 is 50. Add them together, you get 80. Woo! That was cool. That was fun. That was a little intimidating. I was like, what do we do here? Oh, no. We can handle it. All right, guys. Thank you for sticking with me. We got 2 more problems. I know this one's getting a little lengthy. I say that sometimes, but I promise you it's going to be all worth it. Some advanced solving to finish it out. We're going to do 2 examples of this because it is rather challenging. So I've got this problem, 3 to the 2x plus 3 to the x minus 20 equals 0. What the heck am I supposed to do with that? Well, first I'm going to look at the 3 to the 2x, okay? Now, and I could write that as 3 to the x squared, right? I'm using my exponent properties. Power to a power means multiplying the exponents. So I'm just kind of going back the other way with that. And then plus 3 to the x minus 20 equals 0. Now, you may have heard of this fancy thing called U-Substitution. We picked this variable u because we rarely use the letter u, the variable u. And I could let that equal u equals 3 to the x. Okay? And what I'm going to do is I'm going to substitute u in, U-Substitution, in for the 3 to the x's. So I'll have u squared, that's a weird u, plus u minus 20. Well, what does this look like right now? This looks like a quadratic. It's a little factoring problem. No big deal because we rock at factoring. So I'm going to have u plus what minus what? Let's see here. Plus 5, u minus 4, what multiplies to negative 20 and adds to 1. We've got it. There it is. So u equals negative 5 and u equals positive 4. So I'm done, right? No. That's what u equals, right? But u equals 3x. So now I need to have 2 separate ones here. We'll start with the 3 to the x is equal to negative 5. And I'm going to have 3 to the x equals 4. 3 to the x equals negative 5, and 3 to the x equals positive 4. How do I solve this? I don't have a x root, like to square root and figure out things magically. Oh, no. Wait. I'm looking for an exponent, right? And I believe I've said 80 million times that logs are exponents. So perhaps if I put this into log form, get me an exponent. Let's do it. Loop and swoop. If you're a loop and swooper. I'm a loop and swooper. Mr. Thornley showed me that one way back in the day when I was first teaching logs. I haven't gone back. Love me some loop and swoop. So I have log base 3 of negative 5 is equal to x. Wah, wah. What can we not take the log of? A negative. It's got to be greater than 0. The argument has to be greater than 0. Not going to happen on that one. Yay! I get to skip over that problem. So now over to this one. Log base 3 of 4 is equal to x. You are going to need a calculator for this one. So let's do that. So I got my calculator over here. Oops, didn't mean to hit the alpha there. So I'm going to hit math, alpha, math. Uh-oh, does this one not have it? No! There should be one more option there, which would be option A. If you have math, alpha, math, yours will pop up a lovely log button, but mine does not have it. So guess what? I got to use change of base. So I'm going to hit log of 4, close my parentheses, divided by log of 3, close it. I will get the same answer you did, which is 1.2618, so 1.262. Cool. X equals 1.262, approximately equals, so it should be a squiggly equals there. There it is on that one. Again, if it's math, alpha, math, if you have the newer TI-84s, but if like even some of the 84s don't have that, like this emulator here, some of them don't, and the TI-83s definitely don't. So change of base is your friend there in that case. All right, let's do one more there. Change of base is your friend in that case. That was good. I like that. That was fun. All right, a little weird looking here, isn't it? Let's see here. So it looks like a nice ending to our lesson here that has gone on a little long. 25 to the x. I could write, and I got 5 to the x. So I'm already thinking here, I'm like, hey, man, maybe I can change that up a little bit. Couldn't I write 25 as 5 squared to the x, which would be 5 to the 2x, and then I'm going to rearrange that again and get 5 to the x squared, because I kind of have an idea of where these types of problems are going now, that I can be strategic in that. How many of you were tempted to multiply 3 and 5? None of you, because you know you can't do that. All right. It's got an exponent on it. It's got an exponent. Gotta obey the exponents first. Give them respect, okay? Multiplication comes after. All righty. Well, now I have a 5 to the x and a 5 to the x, so how about we let u equal 5 to the x, and I can go ahead and do my little U-substitution fun. So I have u squared minus 3u, ooh, a coefficient, that's cool, that's cool, minus 4 equals 0. If I factor, what multiplies to negative 4 and adds to negative 3? Well, that would be u minus 4 and u plus 1 equals 0. U equals 4 and u equals negative 1. Okay. So now that I got my u's, I'm going to set them equal. I'll change colors now. I'm going to go with blue again. So I'd have 5 to the x is equal to 4, and I'll have 5 to the x is equal to negative 1. So I'll have log base 5 of 4 is equal to x. And if we plug that into our calculator, drum roll please, 0.861. There we go. Squiggly equals, because I rounded. Lovely. Now this next one, you might already be like, hey, Mr. I know what's going to happen. Log base 5 of negative 1 is equal to x. That is my argument, my negative 1. I cannot take the log of a negative. We know that. That one's gone. Finito. This is our only answer. Whew. That was intense. That was fantastic. We logged some good math hours there. All right. I hope you guys have a wonderful day. America, freedom, rock and roll, Costco, members only. Follow Riverdog Jenny on the gram, of course. You guys have a great day. Peace.